So so the questions I had sent, they are not in the right order, and I also did not get one of the questions. So maybe someone who has it can send it. In any case, let's get started with the first question which I had sent. Okay. So here we want to show. So this is the so just to this is yesterday's ISI. So this is ISI 21, right? 2021 subjective, right? We are trying to discuss this. Okay. So let's look at the first question. We want to show that every rational number, yeah, every rational number show that every rational number, okay, can be written as in terms of these factorials as the denominators, and finite sum as a finite sum of this kind. 4 factorial and so on. There is an by n factorial, where obviously we have condition on weights, and these conditions on weights are usually for uniqueness. So we want the an to not be more than n minus 1 and can be 0. Right. So finite sum, and also we want to show uniquely. Okay. Yeah. So let's first see what people have tried. Anyone wants to say what they have tried? Oh, sorry, 1 minute. My audio has some problem. Can you guys hear me? Hello, can you guys hear me? Sorry, 1 minute. Ah, yeah, now can you guys hear me? Hello? Sorry, 1 minute. Huh? Can you guys hear me now? Yes, yes, sorry. There was some. Okay. So tell me, how did you guys try this? Yes, right. So we can assume that the sum is m by n. Okay. Sorry, 1 equals? Oh, what are you transforming? The A1? Oh, sorry. Yeah. So that leads to this. Okay, let's see. Yeah. Oh, okay. So, okay, that's an interesting approach. So you're trying to interpret this as a probability of something. Okay. So how do you interpret that? Uh-huh. Okay. Uh-huh. Sorry. M is the total, because that's the denominator. So M is total number of balls. Okay. Okay. N is the number of red balls. Okay. Right, that's okay. Yeah. Sorry, if we choose two out of what? Okay, choose two out of the n. The but what is the r? Okay. So r is just something whose range is between 2 to m, and you're choosing 2 out of r. Okay. Okay. Right. Okay. Mm-hmm. 1 minute. So, what is this calculating? So, out of r, you're choosing 2. Right. Okay. Then you want to add this up over r. Okay. Okay. Times the probability. But then why should this be 1? Or should this, do you want this to be 1? Okay, that is, but I'm not convinced. How is this? So, what is the event? Sorry, what is the experiment? So, experiment is just to picking. Uh, what is the experiment? Yeah, that I need to understand first, right? That is not well defined, right? What is the R and what is the? I mean, for the experiment, like, what is the experiment? Picking one red ball is not an experiment, right? Yeah, that is, yeah, that's why I'm very doubtful of this, but it might, you might make it work. I do not know. But as of now, I don't understand the experiment very carefully. But this is a very creative idea. It's a new idea, right? Okay, so we'll think about. I'll try to see if I can do something with this. So you should also think, but make the experiment make the experiment more clear. Then you will know if there is any, if this is will work or not. You will know better if you just make the experiment more clear. The experiment should be like, you cannot say the experiment is picking a red ball. That is not an experiment. The experiment can be something like picking up 2 balls or 3 balls, or like, you cannot determine which ball you're going to pick. That's not a random event, right? So try to frame it different way. But you see, this is a question which is just in the topic of representing a number with special kinds of weights. Okay, so I'll just say a little bit of thing around it also, and then we'll try to solve this. Okay, this is basically representing a number using specific weights. In the usual, what do? We use powers of tens, right? We use 1 by 10, 1 by 10 square, and so on. um, I was doing this like couple of weeks back in the Wednesday, in one of the classes on Wednesday, where we were trying to write a number in terms of what are these are known as Egyptian fractions. Every number can be written in this way, right? In a finite sum. And then there was another question which is there in this kind of topic. Obviously, there's one where you write it with respect to different base. That is quite a well-known one, right? You can pick, let's say base 2, right? So you can, yeah, you can pick a1 and then in base 2, and so this may not be finite even for rational numbers, and so there are conditions and so on. But then this, and then there was the third type which we had discussed in the class 2 weeks back, and this was, and you guys can try all this also, there's problems around this, okay, for those who have not, was the following, right? Given a number like this, you can write it in the following way as a finite sum. Okay, it's roughly, I believe, should be like this, as this, and then you use, and of course here there will be some I don't know, n1 maybe. Okay, this will be a1 plus 1 n2, and then there is n3 a1 plus this, and so on. And this also will be finite for a rational number. For an irrational number, it will actually converge to that irrational number. Okay, so these are the problems which we were looking at, and this is like one of those questions. Okay, it's like a special case or whatever of this. And there is a fundamental way to attack all these questions. Okay, there is one fundamental way to attack all this question, and that is to use a greedy approach. This is a topic which we are exploring more in graphs class also, but yeah, the greedy approach. Okay, and this, and there are several other representation of a number using specific kinds of weights, which all are attacked by a greedy approach. Now, what does greedy approach mean? Well, the greedy approach means that at each step you try to make the best choice at that step without thinking about the future too much. Just make the best choice at that step. Okay, so what would it mean in this case? In this case, it would just mean that your n1 should be picked in a way that n1 is 1 by n1 is less than m by n, but it is the best n1, which means that 1 by n1 minus 1, which is just the next bigger one, is bigger. So you're choosing the best one. All right, you choose the best one, and here also you do the same, and even here in all these things we just choose the best possible at each step. And then you want to show, then take the difference, subtract, take the difference, and on the residue you do the same thing. But then the main thing to show is that it terminates, and then you have to find something that actually decreases, and so you can use that to say that it will terminate. Okay, so try this try these questions with this, but let us specifically do this question because even I have not done it, but I think it should just work by the same approach, okay, which we have. Okay. And I think this question was one of you had asked me long time back also, this question mail. In any case, let us try it with that approach. So what does it mean? What does it mean to apply greedy approach in this case? I mean, this just means that you choose the best A1. Okay, choose the best A1. And what is the best A1 in this case? Right, the best A1 is, well, there's a called the floor function, right? But we will just write it assuming we don't know anything, just like this, that is m by n. This should be bigger than A1, bigger than equal to. If it's equal to, we are done, but it is less than A1 plus 1. This is what you choose at the first step. Okay, and then what should we do? Obviously we'll subtract, right? So we subtract, I think we'll just subtract, and then we want to do the problem for this. Yeah, but the key is that you have to show the termination. Okay, I do not know how to do that in this case. We can, when we do, we'll understand. A1 can be 0 also. Yeah, A1 is an integer. Yeah, that's what, yeah, A1 has to satisfy this. It's the best A1 that you can choose. Yeah, these AIs are all integers. I'm sorry. Yeah, they are all non-negative numbers, and they are of this kind, right? Sorry. Yeah, right. Oh, that is fine. No, that is okay, right? I mean, less than equal to n minus 1 means what? No, but then, I mean, okay, that's the condition. Hold on. No, but that was for, No, that is for, so you see the, okay, so I didn't write it clearly, right? It's my fault. For n bigger than 1. I'm sorry. Otherwise it will not work. Otherwise you will never be able, otherwise this number is very small if they have this condition. Yeah. So this condition only applies from A2 onwards. So sorry for not mentioning that. Yeah, that was, yeah. Okay. All right. Let's move on. So now please tell me, someone tell me what should we do as in the next step? M by n minus A1. Oh yes, yes, yeah. I and let's call this M1 by N1 or something like that. So yeah, what should we do now? Yes, yeah, right. And I'll just say it in the old language. So we just reduce the question to the previous case. So there's literally nothing new. This is exactly how division algorithm works. The Euclid's division algorithm is exactly this. If you try to execute it without using the algorithm, if you try to find decimal expansion, it's all those questions I mentioned and this have the same, right? And then this becomes this from, so the two goes, right? Two goes away, and this becomes 4 into 3 and so on, and this becomes uh, from, sorry, 3 to n minus 1, n, sorry. Yeah, we could just use the box language, but yeah. And then again we will choose a A2 to be the floor of this, right? So let me just write it in the basic language. The A2 that we choose has to be less than or equal to this, and this has to be less than this, right? And in this way we continue, right? Then continue in the same way. What do I mean? Just consider the residue again, subtract by A2 and then multiply by 3 and do it, and 4 and do it, and so on. Okay. But so good. But then what is the guarantee that this will terminate? Question is that, right? Why should this terminate? And by the way, this condition is met by this. You can easily verify, right? When way we are doing it, this condition will be met, right? Because m1 by n1 is less than 1, and so 2 times that will be less than 2, so a2 will be less than 2. And similarly, every stage every stage the residue is going to be less than 1, and so when you multiply by a n minus 1, it will be less than n minus 1, so an will be less than n minus 1. That is something that you can just check. But the real question is, why should this terminate? That is something which one has to think about. No, that is not a guarantee, right? So bounded and increasing or bounded and decreasing, just if you just mention, yeah, this is a fallacy which a lot of people make. I mean, we all make at some point. Bounded and decreasing. That is certainly the case in this situation. Yes, I agree. It's bounded and decreasing, but that doesn't imply that it will terminate. You can write any you can write many sequence of rational numbers which are bounded and they decrease, but then they don't terminate. Like 1 by n is a typical example. Here you have to show something, some integer type of quantity, which is bounded and decreasing. And you will definitely find that you'll definitely find that if you just take an example, you will clearly see what is actually is decreasing, and that differs from problem to problem. Like the other problems I mentioned, in all the different kinds of things decrease, but every time they decrease and it terminates. But what happens in this case? How do we show that it? What is the quantity that is just going down? So bounded and decreasing is not enough. So this is not enough. Okay. So let me just mention this. Uh, take examples and find a decreasing, I can call it decreasing invariant and so on, just decreasing parameter. But remember that decreasing parameter should be of a very special type. It should be like an integer, okay, like a decreasing parameter of integers. Okay. Once you take an example, you will understand what is decreasing. Okay. But in this case, my hunch is that the numerator is decreasing, right? If I look at the numerator, let's check that. So is m1 less than m minus a1 times n? No, sorry, that is what it is. Is m minus a1 times n less than, no, that is obviously 1 minute. Yeah, so I mean that is obviously less, this is obviously less than m, right? So at the first stage, automatically the numerator is decreasing. But obviously you want to show that this happens at each stage, right? So what do I mean? So you have to show that, let's say at the kth stage you had mk by nk, and this was less than 1, right? And what would you have done? You would have multiplied this by k plus 1, right? That's what you would have done, right, at the kth stage. I mean, the best way to do this is to take an example and see what actually goes down, but I just want to see if this will work. You would have multiplied this by this, right? And then what would you subtract? You would subtract an AK, or you would subtract the AK plus 1, right? Yeah, is this good? This is what you would, this is what the MK plus 1 will become, right? MK plus 1 by NK plus 1. This is what it will become. Obviously, it may cancel things and it may simplify, but this is what it will become. But then the key is that you're choosing the best one. You're choosing the best one, which means that the k plus 1 times mk by nk is less than ak plus 1 plus 1, right? And it is bigger than ak plus 1. You see, this is how we had chosen it, right? And then, I mean, this is just a matter of translation. From here, you can show then that this is going to be less, or not this, but just a numerator. So again, just a rational decreasing sequence is not enough, right? The claim is, and hopefully this will work. If it doesn't, then we have to just take an example and find a simple invariant. Some other will work then. But the claim is that this numerator, which you get in the k plus 1 at stage, okay, is going to be less than the numerator which you had at the kth stage, which was mk. Right? And this is just translating the definition, right? So you can do mk, you get a k. This is less than ak plus 1 times nk. I'm just translating this, it's the same thing. And then you divide, and you have this thing is less than ak plus 1, right? And right, and this is and we are done, right? Because now if you just add a mk by nk on both sides, you get this inequality. Rather, you get something better. Let's just write it. So the claim that the numerators are decreasing is true, and you may not see this immediately because you have not done problems like this before, but you may not have. But if you just take an example, then you will see it's true, and then proving it is very easy by using this. But you have to be consciously knowing that you're taking the best possible. Just taking the floor and all, you may get lost in the notations. Okay, you have to consciously know that you're taking the best one. Okay, so what we are getting is, I mean, what my claim that the numerator is decreasing is reducing to this. So this is where we are. Right? The claim that the numerator is decreasing is reducing to this, but then it's very simple. You can just add a mk by nk on both the sides, but we know that mk by nk is less than 1. So this is obviously less than ak plus 1. And this is exactly this. So you see, making the best choice was important. And that's how you get it. So the numerator is decreasing. And the numerator is a sequence of integers. And that decreasing is what terminates the algorithm. So it's just the greedy algorithm which terminates. And you have to find a parameter which terminates. So really this question is, I've not done anything. I've not literally not done anything. I've just taken the best things at each step. I've just taken the best things at each step, written it down properly, and then found a parameter. And it works here, but it works, as I've said, just saying it again and again, but just want to say it's a very simple question. Okay, that it works here, and it also works in all these questions, and there are many more questions. Okay, any number can be written as uniquely sum of Fibonacci numbers. All the questions, this same technique will work. Choose the best at each step, and just use that it's the best to show that the decreases. And if to find something that decreases, but that you will know if you take examples. That what parameter? Try to do these questions also in the same way. These are all easy. Okay, so I'm very happy that this question, which I just discussed on Wednesday, just came up in this exam. So should we move on? I think I said more than what was needed. Let's move on. Let's try more questions. I was very confident of this question, so I put that first. Let's try the other questions which I'm not very confident of how to do. Um, yes, let us try the next question. This is about a functional equation. Yeah, let's write it. Let's write it clearly. Let's not rush. So this is a function from integers to integers, and there is, this question is not that good looking. Anyways, f1 is 0, and then we have two conditions. Two conditions. Let me write it. I don't remember the exact number, but this is, for me, it was number 2. That's how I found it. So this is condition number A, and then we have another condition, which is it's a very contrived looking condition. Okay, okay. We want to find the range. Okay, we want to find the range of f. That's what the question is. Okay, so the so part one is find the range. So how do we find the range? Let me just check the equations are correct. Yeah, let's try to find the range. So what are all the the codomain is given to be integers, good, but then what's the actual range? Yes, it's a very strange, but that's how it is. It is just what it is. F of x minus y times f of x times f of y is equal to this. That's what it is. I cannot cancel because it may not be it maybe 0 for some values, or I don't know, for most values. But that's how it is. Yeah, I don't know why they have given it like this. That's why I was saying very contrived looking condition. Hmm. can be converted, right? But so don't let us actually find f of 0 first. It's easy, but let's. Okay, okay. No, no, but we don't have to solve it, right? That will be a difficult task. So we do not want to solve. But in any case, yeah, let's. No, see, if you, but that's right. But then you see, they are just asking us to find the range. So the question is determine. So one should read this thing like in the sense that determine this. So this, what is it? Okay, so then that's all we need. Then no, no, but yes, yes, yes. But let me just clarify. Like, see, we do not see there might be two families of solutions, but we are just interested in as a set what is the range. So maybe a lot of people, a lot of students might just try to find the if, but that's not needed. We just want what values are as a set. Okay, then yeah, that we will come to, right? And so let me just first write the claim that is being made, that f of n is equal to 1 for all n, that is for all n not equal to 0. So that is claim. And no, not equal to 1, right? And f of 0, sorry, f of 1 is 0. How do we prove this? So I think some suggestion was made about putting, let's actually do it, right? And also there is a certain language which I here just a way to write bookkeep, which I suggest here. May not be needed. This is easy question probably, but you should use this, like, just look at it as a statement in x and y and then substitute values. That is a language which we used in harder problems. It becomes very convenient. So what should we substitute here? There was some suggestion made to prove the. No, you cannot do that. That is the problem. No, no, you cannot do that. Sorry, x and y are consecutive integers. Yes, let's just put that, right? That's just the easiest thing to do. Yeah, maybe what was being said about consecutive might also work, but yeah, this is just the easiest thing to do, is just put them together like this. And you just from here you just get, because f of 0 is not 0, f of 0 is 1. That's just easy. Yeah, very. Right. So let me write this. This is a very good habit. Will be very useful for harder questions. So just write it. And here you are saying that you just put n and n minus one, something like this. So then you no. Okay. Yeah. Let's do it. But then if you do that, if that is the suggestion, then you get f of n minus one, f of 0, f of n minus 1. And this becomes 0 because f of 1 is given to be 0. This becomes, and f of 0 is 1. We get, hold on, we are getting something strange. So then this claim is not, yeah, then we have to modify it. It's not correct, right? Right. But we have found out f of 0 is 1. So, but yeah, let's divert the focus again to what is being asked. Otherwise, we'll get lost in this. We just want to know what is. So, how do we show that there is nothing else possible? Uh, how do we show that the range is 0 and 1? That is really what it seems like. Hmm. No, no, no. I understand. No, no, that's fine. You choose. So you want to choose x and y which are not. Yeah. Yes, but you see, but this is, I think this is the right way to say it. But if we put x, if we say that choose x and y such that there's not zero, then that may be controversial because such x and y may not exist. Not many of them might. But in any case, this is just easy to say like this. So you do this, and then I think it just becomes easy, right? These are just the obvious things to substitute. Even if you are not paying much attention while solving this question, you just do the obvious substitutions, and you some things will just pop out. Okay, so yeah, we just do that, and we get very simple this thing, f of, right, and then it's from here it's just very obvious that f of x is equal to 1 or 0. So yeah, the first part is done. We will actually try to solve this maybe functional equation, but let's first complete the second part also quickly. So the first part is done. Okay, so the range is 0 and 1, and this is just obvious substitutions. Just do the natural substitutions. That's let's remove these things, okay, because I think everything is summarized there. And maybe the thing about the consecutive was very interesting, but not didn't turn out to be needed here. But in any case, yeah, if needed. So let's do the second one systematically, then can try. So the second part is, yeah, any one. Uh-huh. Right. Uh-huh. Yes, yes, but but one second, let me just write the question. So I just want to say that you want to show that b, f of this, one second, not equal to 0 is infinite. Obviously, assuming that there is a value for which it is non-zero, which you have already found, but you can still do this question by assuming, if even if you're not done part one, you can do this. Okay, so you were saying from the consecutive substitution you can do it. So right, so you mean should I do this n and n plus 1? Okay. No, okay, n and n plus 1. Okay, then I get f of minus 1. Oh, sorry. Yeah, sorry. You put in the equation A. N and n plus 1 in equation A. Okay, so yeah, that's what I've written A. Sorry, not the second equation. So you put this, then you put n. Sorry, should be f of n plus 1 minus fn times f of n plus 1. Okay, if, yeah, this you already know. If fn is not 0, then f of n plus 1 is 0. This you have already seen. Okay. Aha. Okay, okay, okay. 1 minute. So this is equal to, okay, okay, okay. Nice. And this is certainly new. So in this way, you're getting infinitely many things. But there is something. Is this okay with everyone? And, is there something slightly uncomfortable here? Something, because how do you start? What is your starting point? If I ask that question, what is the first n? Oh, non-zero. They have already told. Okay, okay. Then it's, yeah. Sorry, yeah. That is, so. Again, I have to modify the question. Okay, by assuming. Yeah, so that's a very important pick. I missed that. Okay, assuming that there exists uh, a naught or whatever non-zero, such that f of a naught non-zero is important, is not equal to 0. Okay, nice. So then you have this sequence a naught plus 1, a naught times. So this is again like the first question, right? This again, the same sequence is popping up. It's like a factorial sequence, right? It's again, I don't know if they made this from the same kind of. Yes, that's possible, right? So that's it. I think there's this was there in the first question also, which was just they put a not equal to 1, and that was the version which they asked, and this is also the same sequence is used here. So maybe there's something. Okay, so then Noel, you solved the you got some solutions, right, for fx, some more concrete. So, yeah. F of n plus 1 is 0. Okay, yeah, okay. That's okay. Or 0. F of a minus b equal to 1. Okay. We can put you can put b equal to 0. Right, okay. Yeah, that's so this we already know. Yeah, yeah. uh Okay, a. Let's think. So we're trying to actually find a way to solve this, but I think there is two. Mm-hmm. 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 No, for all n not equal to 1. Right, so I can just say this, right? F of n is equal to 1 for all n not equal to, yeah, this will certainly satisfy, but this is a trivial solution. I mean, yeah, this is one possible. Uh-huh. Mm-hmm. No, this will not satisfy. Oh, this will also satisfy, but yeah, in this, yeah, that's right. Oh, okay. No, but that is not true. That is not true. That is not true. No, no, that is not true, because we already, from what one of us already said, right, that fn times fn plus 1 is 0. So that really just it says that it's not possible. So it says that it is not possible that this is the only solution. Yeah, right. Because I mean, in any solution, this should be true, right? In fact, then I'm not even, yeah, then this is also not a solution. Maybe you can check it then, because if we have this, that two consecutive product is 0, yeah, so yeah, 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 so this will not be a solution, so this is wrong. But I Does it? One has to check it. No, no. But then see, if this satisfies, then this cannot satisfy, right? Both cannot satisfy. So then this one may not should not satisfy. You have to just check it. One has to just check it. Yeah, but that doesn't matter. In any case, that doesn't matter, right? Because this is also for a statement for. So these two statements will intersect non-trivially, and then it will not hold. So one of them has to not be true. In any case, I see. I'm highly doubtful that there will be a way to solve this. Okay, from what I don't think there will be a solution. There will be infinitely many because essentially, if you start with, basically, you have to put one more assumption here about, yeah, what is the first thing which is non-zero apart from zero, and that will determine very strange and different solutions. I mean, you could probably say something about the set of all solutions. That set of all solutions might have a good algebraic structure or something, but I do not know if it is possible to. Yeah, that I do not know. Yeah. In any case, let us come to the next question. Let's try the next question. Yeah, let's quickly try. So this is problem 3 in my indexing. So we have these numbers. Let's write the question carefully. So we have seen that the first two questions are simple if we think simply, okay, and just conceptually. And at least for the first question, yeah, so yeah, yeah. So that might be, that's the thing. So it can be. That's why there's no. Okay, let's see. Yeah, let's see. So this is a polynomial. Why have they? Okay, because they want to say. In any case, let's not use this. Yes, it is. It is monic. That's all. That's all that's needed, right? Why have they mentioned all this? So it's just a monic. So P is a monic 20-degree polynomial. That's all that it is. So P is a monic uh, degree 20, because it doesn't even feature in later on these coefficients and so on, not even the index. That's right. Yeah. So then we have this other condition. Yeah. And this automatically says this already says that it will only have even powers. The polynomial, this already says that. Okay, so this is given. This says that it will only have even powers, but yeah, let's see the question. And then and we also have this thing, pk equal to k square, and then you want to find a limit. Okay, so this is okay, anyways, I won't say. Yes, yes, yes. And again, I don't want to say like that, but I think one of us has written mock 5. There was a question like this in mock 5. There was a cos in the denominator in mock 5, but it was not a polynomial, I think. But yeah, so I don't know, it was different. It was not polynomial related. In any case, it was a trigonometric limit with. So yeah, how do we find this? Yeah, no, that is in a different mock, which probably not seen. Yeah, so obviously it's not for all k. Yeah, not obviously for not for all k. Nine. Yes, yeah. So there is this very okay. Okay, let's go one step. Okay, maybe we can speed it up then. So essentially, let me first just mention the technique, because not all of us may have. I don't know. So this is, whenever this is given, this is a polynomial which is given in the unfactored form. Okay, and the idea is, can you convert it to factored form? The way the polynomial is given is in unfactored form, and we want to go from unfactored. Okay, yeah, maybe you can say that, but in any case, yeah, it's from unfactored to factored, right? And the way you want to do is you want to make a polynomial whose roots are known, and so obviously you should consider this polynomial, you should consider this, right? And then dot dot dot, find its roots given the two conditions, find the roots. Okay, so maybe some of you have already done, so can you then tell me what px turns out to be? Yes, so this is just easy. Plus x square, right? Because this was minus px minus, this is the form in which you will get, and this is really comes from the factorization, right? The Euclidean division and all that, that gives this. So this will work in any place where there is a sort of division, where you can do some notion of division and remainder. In any case, this is what it is, and then we want to just uh how do you how okay, just go a little slow. My limit is a little, yeah, so let me write it here, and it's, can you please explain then how you got that? So you click limit. That's right. Yeah, yeah, that's right. When you see this sign, then you do this. Yeah, yeah, right. So from there you can just do this, and then it's very trivial. You can just do it, right? Yeah, no, I don't think so. So this is very simple. This is just polynomial factorization question. Just this technique of, yeah, very simple. Let's move on. No, so I just want to do. So I don't think we can complete all the problems, but I just want to do the seventh question. I don't want to do, but I just want to point out something in the seventh question, which, yeah, I think I did take a look, and yeah, let's look at that. Okay, the other questions in between are, I'm not saying they are all trivial, but they are also pretty easy. And one question I've missed. I don't know where the one other question is. In any case, let's do this because we're out of time. So there are three cities, right? So there are three cities, okay, each having each having n number of people, okay, n people, okay. And I'll just present my perspective on this one first, because I yeah, and then we can see, because certain reasons. So now there are three cities and each having n people. So the way I saw this question, maybe I found an interesting connection of this with something. So there are n plus people in the first city, and let's see if this connection is useful. And there are n people in second city, and there are n people in the third city, right? Each person has n plus 1 friends in the other cities. That's what I was going to say. And more than that, this is a question about triangle free graphs. Okay, triangle free graphs was again a topic which I had discussed some time back in one of the morning classes, um, by in an induction topic, and this was just by that you can do this question. But in any case, let's see. Let's first frame the question. Each person has n plus one friend. So obviously, if so the model is, let me mention it clearly, join 2 points if they are friends. Okay, and also this is also important. We only consider friendship in different cities. In different cities. That's all, right? We want to only do this. So you see, this is a graph. It's a setup of lines and points with three endpoints. There are three endpoints in this, right? And what the observation I made is the following. We had three endpoints in this, and this is what is known as a tripartite graph also, but The idea is that there are no lines in between. I mean, sorry, no lines, inside any circle, right? And you just want to show that there is a triangle. Show that there is a cycle of length 3. There is a triangle. Okay. Now, I don't know if this will work, but yeah, this is the observation I made. And first, let me state that observation qualitatively. Okay. A graph with, we want to show that this is not triangle free. It has a triangle, right? A graph with vertices, too many edges. A graph with too many edges will not be triangle free, will have a triangle. If a graph has too many edges, it will have a triangle. It's an intuitively very obvious thing. Okay. But same question for cycles is I think is very very hard. Okay. For triangles it becomes easy. So what is that too many? Okay. So for m vertices, what is the too many? And that is very simple to prove. If you just take some small graphs, take a graph of size 4, 5, obviously not 2, 3, take some small size graphs and then see how many edges you can, this is just the method I'm describing. See how many edges you can fit in the graph without creating a cycle and see what you get. Okay. And this is what you will get. For m vertices and no triangles, then at most m square by 4 edges. Okay. It is not difficult to prove. Okay, you can just, this is was a topic, this is just a topic in induction. You can just do it by induction essentially. Okay, assume it and then just add another vertex and just just do the case. You don't want a triangle, which means that for any 2 points which are neighbors, they don't have a common neighbor and so on. So you can just try it with induction. Yeah, but this is the sense that you, if you're sitting in an exam, this is the sense, and then you try out some things. And yeah, in any case, this is a very, it's a popular result in graphs anyways. Which, yeah, in any case, this is something that you can prove. Okay, try to prove it. We just want to see if this, I don't know if this will do the problem. Okay, let us put the values in this case. Okay, I'm not saying this is the very best way to do the question, but let's see if this, first of all, let's see if it works. If you may be right, yeah, I might be wrong because this is a special graph. Yeah, you may be right, but let's actually put the values and check it first. Okay, so if you have 3 endpoints, okay, let's see how many edges, okay, number of edges in our case. How many edges do we have in our case? It's 9, no, it's not 9n square by 4, right? It is it 9n square by 4? Because for every person, yeah, sorry, yeah. So it is 3n times n plus 1 by 2. This is the number of edges, and you can just check it. Okay, basically the total number of degrees and divided by 2. This was also what we discussed the last class, that the degree sum is even, can also be proved from here. This kind of this is the most more quantitative version of that. In any case, this is the number of edges in our case. Now, yeah, so you're right, might be wrong. This, and you are allowed to have 9. Sorry, this does not work. Yeah, that's what I was. Yeah. You are allowed to have this many because you have 3n. 3n is the problem. 3n, you're allowed to have this many, and obviously this is more, so this might be triangle free, but because of the more information, it is not triangle free. So it doesn't, so this doesn't work. Yeah. Okay, but in any case, we learned something. Um, So we are out of time, but has anybody tried this? Does anybody know how to do this in another way? Because I've not tried this. Okay, so what do you do? So choose, okay, choose person X, which has maximum number of, yeah, number of friends in another city. Okay, yeah, let's call that X. So if this is X, and let's say in city B he has K friends. Okay, say city B, K friends. Right. So in city C has n plus 1 minus k, and so this k will be obviously more than n plus 1 by 2, but yeah, as n plus 1 minus k friends. Okay, yeah, let's, anyway, I think a1 is a better notation. You are, I think that makes more sense what you're saying. So a1, a1, and there is c1. Okay, all right. Uh-huh. Right, and let's mark this region which is friends of a1. So there are k things here. Okay, right. Okay, so c1, that's right. This is just following the logic, right? Is just comes out. C1 has at most n minus k friends, because again triangle freeness. So you have to, the neighbors of an edge has to be disjoint. That's the nature of it, right? Has to be n minus k, has to be n minus k friends in B. So yeah. Yes, that's right. Yeah. So it's just max, considering the maximal, just the best. Yeah, just the best. Just the best one. Yeah, I mean, and if this can be done by maximal principle, then it can also be done by induction. I think, yeah, because maximal principle is basically going right to the best case, right? But you can also maybe or um, no, yeah, let's leave that because that's not in. No, I might be wrong. This is as easy as it gets. That's right. Yeah. There was another way in which I was thinking is to consider all the local information and add it up to get some global information that is contradicting. Uh, how? Yeah, yeah. How? Huh. Mm-hmm. Uh-huh. Okay. Yeah. Let's try that quickly. So, if no triangles, then oh yes, let's do that. Yeah, that's these are the ways to do these questions. Yeah, I mean, uh, to try this out. So let's say there are three. Okay, then. Mm-hmm. Okay. Right. Okay. Uh-huh. Yes. 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 Yeah, like this. Yeah. Okay. Right. One more. Yeah, there has to be one more, right? Yes. Yeah. No, but then this is the way you are constructing it, right? This particular construction may not be general enough. See, you are doing it in a certain way, right? But your argument, you have to write your argument in a way that doesn't refer to any particular right particular thing, any particular way to join these things. So, but you can try to write, and that's basically what I also had in mind. From locally, you consider, then yeah, then you can do. So basically, yes, basically what I was thinking is that, I mean, for each person, for let's say for this person A1, you look at, let's say um, it has K1 friends in B, or B1 friends in, yeah, B, K1 friends in B, and n plus 1 minus K1 friends in this, and all these local information you have, and then you try to add it in some other way and get a contradiction, something like that. It can probably be done like that. And it can probably be done by induction also. I feel you assume for small case, and then you basically add one person and something like that. Yeah, you reduce it. Yeah, basically for those three people that you add, you can avoid triangle there and then reduce to a smaller case where you will get a triangle. That's how triangle freeness is, and that is similar to what Chandan you are saying in the, yeah, you reduce, you try to make all, because for 3 points that you add in the inductive step, you can reduce to smaller case easily up to the next smaller case, and there you have assumed it, something like that. Obviously for 3 it's easy to prove, and so can be done by induction maybe. Yeah. So I think we are out of time. Let's not do the other three questions. I think they are easier than the ones we have already done. Right? They are just problem 4 about the differential equation thing is, I've just said it. Differential equation very simple, and problem 5 is also, you can just try it. Problem 6 is just pure calculations. I think simple calculations. Okay. In any case, yeah, that's it for today. Yes, yes.